Good morning, students. The topic of discussion for today is gameplay. We are learning how AI system could solve search related problems like traveling salesman problem, water jug problem, cannibals and missionaries problem. Likewise, in this chapter, we will look at how AI would solve a game problem. What is a game? Well, a game is defined as a sequence of choices where each choice is made from a number of discrete alternatives. And there are two types of games: perfect information game and imperfect information games. Perfect information games are those in which both the players have access to the same information. Example, checker, tic-tac-toe, chess, go. These are the games which has got perfect information to both the players. And imperfect games do not have complete information provided to the players. For example, if we have dice games, when you look at the dice game, when you roll the dice for the next time, you will not know what number will come up on the dice. Therefore, it is not a perfect game. In this chapter, we will study discrete and perfect information games. When do you call a game discrete? Well, when the game has a finite number of states or configuration, then it is known as a discrete game. Game problem versus state space problem is the next topic. Please recall that state space problem are those problems which has got a number of states that are joined together into a state space problem. A problem would have a start state and a goal state and a number of intermediate states through which the system would go along the start state up to the goal state. That is a state space problem. Comparison is presented in this table: state space problem and game problem. In state space problem, we have got states, rules, and goal. Game problems would have a legal board positions, legal moves, winning positions. States, for instance, in a water jug problem, when we have a 5-gallon jug and a 3-gallon jug, if 5-gallon jug is full with water and 3-gallon jug has 1 liter, 1 gallon water, that is one kind of state. This has got full water. This has got only 1 gallon water. This is 5 liter. This is 3 liter. This is one state. Likewise, you have a different number of states. Legal board positions. What are legal board positions? If you consider a chess game, yeah, you find a board, 8 by 8 board, and then there are some legal positions that mm, there you have so let us take pawns. So how pawns can move? You have got king. How king can move? But this is with respect to chess. Likewise, you have other board games, and they have got legal moves and also illegal moves. Illegal moves are those moves which are not permitted to take. Legal moves are those moves which are allowed. Rules and legal moves. Here there are rules that dictate how a system move from one state to another state. Here we have got legal moves that specify how uh, elements on the boards can be moved. Finally, we have winning position in game game playing, whereas the corresponding uh, um, concept is goal in state space problem. A game begins from a specified initial state and ends in a position that can be declared a win or a loss for the other, or possibly a draw. Alright, whenever a game begins, it begins with the initial state, and it follows number of moves, and uh, ends with win, loss, or draw. All right. What is a game tree? We have developed DFS solutions, also represented problems like what is your problem in the form of a tree. Similarly, game tree is a explicit representation of all possible, uh, moves of the game. The root node is the initial, and there are successors of the root, and wherein the first player can reach, uh, from one move to another move. And there are terminals. Terminals are the leaf nodes that denote either win, loss, or draw. An important point here is that game theory is based on the philosophy of minimizing the maximum possible loss and maximizing the gain. Okay, minimizing the loss and maximizing the gain. In game playing involving computers, one player is assumed to be the computer, while the other is a human. And during a game, two types of nodes are encountered, max nodes and min nodes. Max node will try to maximize its own game while minimizing the opponent's game. Alright, max and min. We have max nodes and min nodes. We have max nodes and min nodes. Max nodes try to maximize its own game at the same time minimizing the opponent's game. Here the aim is to make the computer win the game. And so computer is actually the max computer is trying to maximize its uh, uh, its game, score. It is trying to increase its score at the same time decreasing the score of the opponent. And status labeling. How is the status labeled in a game tree? We have got win, loss, draw. If J is a non-terminal max node, status of J would be win if any of the J's successor is a win. Consider this tree. If J if J is a non-terminal means which is not a leaf. Consider this to be J. J, uh, here you can label this J as win if any or any of the J's successor is a win. From here, if this way, if there is a win, the other way there is a win, or the third way or fourth way, there are four routes from this. If any one is leading to win, this J node can be labeled as win. And consider this J non-terminal node. This is labeled as loss. When all the successors leading to loss, if all these four terminals are labeled as loss, only then this could be labeled as loss. Draw, in which any of the J's successor is a draw and none is a win. Any one, from here there are four successors. If any one successor is a draw and no other successor is a win, then this node is labeled as draw. Please remember these rules. First, win if any one successor is a win. Loss when all the successors are loss. Draw when any one is draw and there is no win. And if J is a non-terminal minimum node, nodes can be min nodes and max nodes. There is a max, which is a computer playing the game against the opponent. All right. Win. Status of J. Consider this to be J, which is a non-terminal for min. These are terminals. When can you declare win? When all J's successors are win. When you call this as J, if successors are 2, if both are winning, only then this J would be called winning. Any of the J's successor is a loss. If even one of the successor is a loss, it means that J is a loss. Draw. If any of the J successor is draw and none is loss. Either one, any one is D and none other nodes are having a value L. Only then you can call it a draw. These are the rules with respect to max and min nodes. Consider this game tree in which max plays first. This is max. One layer is max, another layer is min. Another one is max, and finally you have min. So you can see here there are labels attached to this game tree. Max, min, max, min. These are levels. And complete game tree with max playing first. When max plays first, max would win. Why max would win? Because max would take this uh, direction from max here, min to this, from here to this max, and from here to this win. There is a win. The successor of this direction is a win. Therefore, this max is said to win the game. How this is built and how it is traversed, we will look at. Here, min is playing first. You observe here the level has been changed. Here it is min max because min is playing first. Min is playing first and min is losing here. When min travels through this path, max is loss and min is loss, and here terminal, it is loss. There is a game called Nim Game. This is actually a game, a real life game, in which there are two players. This game is believed to have been originated in China, and it was brought to Harvard University. There they have developed a complete theory for the Nim game in 1901. There are several versions of Nim game. Here, for the purpose of study, we will choose one version, which is the simplest version. And what is the game here? There is a single pile of matchsticks. You know, there are matchsticks. You have a pile of matchsticks. And there are two players. Moves are made by the players alternatively. Player 1, player 2. When player 1 makes a move, Then player 2 waits. Alternatively, this process continues. Player 2 makes a move, player 1 waits. And in a move, each player can pick up a maximum of half the number of matchsticks in the pile. Whoever takes the last matchstick loses. If there are 10 matchsticks, they should take maximum of half the number. They can take 5. Then when 5 are left, they can take, you know, half of this 5. Maximum the half the number. You can, if you take it, if you consider to be 3, 3 if you take, 2 will be left. When 2 is left, one player will choose 1, another player will have 1 remaining. So whoever gets the last matchstick loses the game. This is the game. Consider